Dear classmates, welcome back to the last video of the Combinational ATPG chapter. We already know that Combinational ATPG is an NP-complete problem, so it is very difficult to solve. We need many acceleration techniques to speed up ATPG. In this chapter, we will introduce two famous techniques to speed up our ATPG. One is learning, proposed by Schultz in 1988. The other one is redundant fault identification, proposed by Euler in 1996. So learning is a technique to memorize circuit information so that we can speed up test generation. There are static learning and the dynamic learning. The static learning is performed in the circuit preprocess stage, so no test pattern is required. On the other hand, dynamic learning is performed in the test generation stage. Dynamic learning is more effective but consumes more CPU time. So dynamic learning is not included in this video. We will focus on static learning in this video only. Now we will show a static learning example from our textbook. Given this circuit, suppose we set f to 1 and we apply forward implication. We would get x equal to 1. We know this very well. However, if we apply the control positive law, we can also learn that in the backward direction, if x is equal to 0, then f must be equal to 0. This is because the control positive law states that if P implies Q, then Q prime implies P prime. In this case, P means F equal to 1, and the Q means X equal to 1. So we know that Q prime, which is X equal to 0, implies P prime, which is F equals to 0. This information is very useful for ATPG because this is in the backward direction. Now let's see how the learning technique can help us to reduce number of backtracks. Suppose that we don't have learning and we want to generate a test pattern for W stuck at 04. So our objective is W equal to 1. Now we can assign H to 1, A to 1. Our next objective is we want to propagate the fault effect to the primary output. So we want X to be 0. Suppose we don't have any information about the circuit, so we would perform backtrace to CD and also to B. So we would assign them to be 0. But actually, this is a conflict because Y would be equal to 1, which would block the propagation of the fault effect. So we need to backtrack. Suppose our last decision was B equal to 0. So we would flip the value of B. But again, this would be a mistake because X would be flipped to 1 and we would block the propagation. So this is also a conflict. And then we will flip D and we flip C. Those are not going to generate any pattern. And we flip A, and then we flip H. Eventually, we will find no test for this 4. As you can see that we have to backtrack many times before we can find that this 4 is actually untestable. Now, let's see the case with learning information. Suppose we have learned this circuit. In the center part, in the gray area, we know that when X is equal to 0, F must be equal to 0. This is already learned in our preprocess stage. During the ATPG, we now want to generate a test for W stuck at 0,4. Our objective is W equal to 1, so we will assign H to 1 and A to 1. And then we want to propagate this 4 effect to the primary output. So now our objective is X equal to 0. Because we have the learning information about this circuit, so we immediately know that F must be equal to 0. In this circuit, we will backtrace to B, so we assign B to 0. But this would be a conflict because Y equal to 1 will block the propagation of the 4 effect. So we backtrack to B equal to 1. Again, this would block the propagation. And eventually, we would find no test. If we compare the number of backtracks with learning and the number of backtracks without learning, we can see that there are more backtracks if we don't have any learning information. This example shows that learning provides valuable information to make correct decisions and reduce the number of backtracks. At the beginning of this chapter, we say that ATPG is a huge decision problem. In this very large decision tree, we want to prune impossible subtree as soon as possible, and we want to find necessary assignments as soon as possible. Suppose that we want to make the decision where X is equal to 0. Based on the learning information, we know that F equal to 1 is impossible, so we can prune this subtree, and we would immediately search for the subtree where F is equal to 0. So, learning provides a very good trade-off of memory for runtime. This sounds a very good idea, but the fact is that there are too many information to learn. How can we select which information is worth learning? This is a good question. Let's see this example circuit again. Suppose we set F equal to 1. We can imply that J is equal to 1. Obviously, we can learn that when J is 0, F must be 0. But this is not a very good learning information because this involves only local backward implication. We don't need to memorize this information since we can directly perform backward implication during ATPG. So this information is not worth learning. Similarly, when F is equal to 1, we can imply K equal to 1. This information is not worth learning. However, when F is equal to 1, we can imply that x is equal to 1. So x equal to 0 can imply f equal to 0. This is a global implication that cannot be implied using any previous technique. So this information is worth learning. Now the question is, how can we decide which information is worth learning? In the Socrates ATPG, they propose the following algorithm. In the preprocess phase, we set all the signals to 0 and we perform implication and we analyze the result of implication. Then we assign f to the opposite value 1. Again, we perform implication and we analyze the result. So the Socrates system provides two criteria to select useful information to be learned. For every signal x whose value is not unknown, we check the gate input value of signal x. All of the signals must be non-controlling values. For example, the gate input to x are 1, which are non-controlling for the AND gate. So it satisfies the first criteria. And then we check the second criteria, where there must be a forward path from f to x. And we satisfy both conditions. Then this information is worth learning. So we would save this information where Vx is equal to 1, so Vx prime is equal to 0. And the value of f is equal to 1, so V prime is equal to 0. This is the control positive law. Now we understand the learning principle. Let's do an exercise. Given this circuit, let's set the value of E to be 0. What can you learn about the K using the control positive law? The second problem, if we want to detect K stuck at 0,4, what's the value of E? Please use the result from question 1. Now pause the video and work on this problem. Okay, are you done yet? If E is 0, then J is 1, by implication H is 0, so that we know K is 0. Using the control positive law, we know that K equal to 1 implies E equal to 1. For question number 2, if we want to detect K stuck at 0,4, then we want to set the value of K to 1. By the learning result, we know that E must be 1. Have you got it correctly? Before we finish this topic, we have an interesting FFT for you. Actually, in our previous quiz, the example was not a good learning. If we set the value of f to be 0, then we observe that one of the NOR gate input is controlling, so it does not satisfy the criterion of the Socrates algorithm. So this information would not be learned if we apply the Socrates algorithm. So why is the reason that Socrates requires both inputs are non-controlling? Please use this circuit as an example to answer this question. And question number 2. Why does the Socrates algorithm require that there is a forward path from F to X? These two questions are interesting for you to understand the learning technique. Please think about them. Now let's move on to the next technique, redundant fault identification proposed by Euler. As we can see from the previous example, proving redundant fault is a difficult task. For example, we need many backtracks before we can prove that this fault is untestable. If we run ATPG on this fault, we will waste a lot of time. So, can we find a smarter way that we can identify redundant fault faster? A redundant fault is also called untestable fault, which are faults that cannot be excited, or faults that cannot be propagated, or faults that cannot be simultaneously excited and propagated. So why do we need redundant fault identification? The first reason is that we want to speed up ATPG. We don't want to waste time on those untestable faults. The second reason is that we can simplify our circuit and reduce our silicon area because redundant logic can be removed from the circuit. Unfortunately, to prove a redundant fault is an NP complete, so it can be worst case very difficult to compute. But a good news is that typically for most applications, we don't need to identify all the redundant fault. So, in 1996, Euler proposed an algorithm that can quickly identify some of the redundant faults. It is called fault-independent redundant identification. This is based on single-line conflict analysis. The idea is very simple. First, we set a signal S to 0, and S1 represents the set of faults that are untestable when signal S is equal to 0. Then we set the signal S to 1. We can obtain another set of faults that are untestable when S is equal to 1. And then we can take the intersection of two sets, S0 and S1. Those sets of faults are untestable because it is untestable when S is 0, and it is also untestable when S is 1. So the intersection represents the set of faults that are untestable in any cases. To find an excitable fault, we need forward implication. To find an observable fault, we need backward tracing. The advantage of the fire algorithm is that it can be finished close to linear time for one signal. Here we have a question for you. Can we solve an NP complete problem in linear time? This is a food for thought for you. Now let's see a fire example. Given this circuit, first we set the signal B to 1, which implies B1 equal to 1 and the D equals to 1. and x equal to 0 and z equal to 0. Now we can find the set of faults that are unexcitable. The faults are excitable when the value is the same as its stuck value. For example, B stuck at 1 fault is unexcitable because its stuck at value and the good value are the same. Similarly, B1 is unexcitable, B2 is also unexcitable, and then D stuck at 1, X stuck at 0, and Z stuck at 0. So this is the set of faults unexcitable when B is 1. And then we can identify those faults which are unobservable when B is equal to 1. For example, in this circuit, the fault on A is unobservable because the side input B1 is a controlling value for this OR gate. So if we backtrace, A stuck at 0 is unobservable, A stuck at 1 is unobservable. Similarly, D is a controlling value for this NOR gate, so those faults on E1 are unobservable. And the value of X is 0, which is a controlling value for this AND gate, so Y is unobservable. Don't forget, we can also backtrace to the input of the inverter, so E2 are observable. Now we have a fan-out branch. Since the faults on E1 is unobservable and E2 are unobservable, so faults on E is also unobservable. Then we can backtrace to C. So the faults C stuck at 0 and C stuck at 1 are both unobservable. Also, the faults on B2 are unobservable. Now we have a fan-out branch. So is the fault B stuck at 0 unobservable? The answer is not, because B1 is observable. So we can make any conclusion about the fault on fan-out stem. So the answer here is that it has 2 branches, and one of them is observable. So in conclusion, we now can have a union of the above 2 sets, S1, which represent the set of faults untestable when B is equal to 1. Now let's set the same signal B to 0, which implies B1 and B2 are both 0, and E is 0, Y is 1. So B stuck at 0, B1 stuck at 0, B2 stuck at 0, E stuck at 0, E1 stuck at 0, E2 stuck at 0, and Y stuck at 1. Those faults are unexcitable when B is 0. And then we find the faults unobservable. Those faults on C are unobservable because B2 is a controlling value for this AND gate. So C stuck at 0 and C stuck at 1 are unobservable. For this AND gate because Y is non-controlling, so the faults on X are potentially observable. Now, we can take the union of the above two sets. So this is S0, and we know S1 from our previous slide. So we now take the intersection of S0 and S1. So now we have a list of faults which are untestable. For example, Y stuck at 1 is in the set of S1. It is also in the set of S1. So it is untestable fault. Now we have an FFT for you. We said that Y stuck at 1,4 is untestable. Can you use the PODAM algorithm to find the test? Please prove that Y stuck at 1 is untestable. Question number 2. We mentioned that redundant fault identification is an NP-complete problem, but fire algorithm claims that it is close to linear time. Can we use a linear time algorithm to solve an NP-complete problem? Of course not. So please explain what is wrong here. Now it's time for you to work on this quiz. Given this circuit, please set the value of B to 0 and 1 and find which faults are redundant. Now please pause the video and work on this quiz. Now, have you finished yet? The answer is like this. When B is 0, we can see that L is 0, F is 0, and J is 1, and the K is 1. So these faults are unexcitable. And since J is controlling, so the fault on H is unobservable, and the fault on A is unobservable, and the fault on L is also unobservable. Now we change B to 1. We can have 1 here, 1 here, 1 here, 0 here, and K is also equal to 1. So the fault unexcitable is in the list, and the fault unobservable is in this list. Those faults that are in gray color indicate that it also appears in the other 4 lists. Finally, we take the intersection of these 2 lists and we obtain a list of faults which are redundant. For example, K stuck at 1,4 is redundant. If we want to control K to 0, we would need both H and J should be 0, which means that B should be 1 and 0 at the same time. So it's a conflict. So we cannot control K to 0. Have you got it correctly? Now let's make some concluding remarks for this chapter. In this chapter, we have shown that ATPG is an NP-complete problem, so we need many acceleration techniques. In this video, we have shown 2 techniques. Static learning is a trade-off of memory for runtime. The idea is to set all signals to 0 and 1 and imply other signals. We can apply contrapositive law to obtain some important information so that we can make quick decisions. And the number 2 idea is redundant fault identification. which is based on single signal analysis. The idea is to set the signal to 0 and 1, and we find those unexcitable or unobservable faults. A redundant fault is the intersection of two sets. Actually, there are many other acceleration techniques available in the papers, and we don't have time to go through them one by one. If you are interested, please refer to the corresponding papers for more details. This picture shows an overview of the ATPG system. At the beginning, we will perform pre-process. For example, we can do learning and redundant fault identification. With this pre-process, we obtain important information so that we can speed up ATPG later. And then, in this loop of test generation, we select a target fault, we run a deterministic test pattern generation. For example, it can be a PODAM algorithm, fan algorithm, or SAT-based algorithm. After we generate a test pattern, we can fill the unspecified bits and run for simulation. For example, parallel pattern single fault propagation or concurrent fault simulation. And then we drop the detected fault. We remain in this loop until we are satisfied with the fault coverage or the time is up. Then we move on to static test compression, which will be discussed in the test compression chapter. And then we finish the test pattern generation. So after ATPG, we will obtain a report. This slide shows an example of ATPG report, and I will show you how to explain this report. This column will show the number of uncollapsed faults. On the right hand side, we show the number of collapsed faults. And ATPG will tell you the number of detected faults and the number of redundant faults. Those faults are proven to be redundant by the ATPG. So we know that for sure they are untestable. But since ATPG is NP complete, there are some faults that we cannot prove them to be redundant. We cannot find test pattern either. So they belong to this category. And then we can calculate the fault coverage, which is the number of detected faults over the number of total faults. We can also calculate the ATPG effectiveness, which is the number of detected faults plus number of redundant faults over the number of total faults. Finally, the ATPG report will show the number of test patterns and the runtime. Of course, these two numbers should be as small as possible. So this concludes our ATPG chapter. This is a very important topic for VLSI testing. So please spend some more time reviewing all the videos before you enter the next chapter. Thank you.